Hello, and welcome to Lecture 17 of AMAT502 at UAlbany. Today, we're going to visit our first example of a dimensionality reduction technique, known as principal component analysis, broadly known as PCA. Let's go through a quick recap of what we're going to cover. So, principal component analysis is this beautiful example where we need to blend both concepts from linear algebra and probability. So we're going to go through a lot of review of that before actually leading up to the main ideas behind PCA. This will connect with some notions of projection and other things from geometry, which hopefully is all familiar to you. So as a quick recap, remember that we have sort of four main branches in traditional machine learning. We have supervised learning, which deals with labeled data, and we have unsupervised learning, which deals with unlabeled data. We've already given examples of regression, classification, and clustering via just linear or polynomial regression. Then we did some linear classifiers, and also we covered the basic notion of k-nearest neighbors classification. We also did a basic clustering example known as k-means. And today's going to be our first example of a dimensionality reduction technique. You can see that we're slowly working our way through this tree of machine learning, supervised with regression, linear regression. Additionally, with classification, we went through k-nearest neighbors. Now we're going through unsupervised learning. We did some of our basic k-means algorithm. And then today we're finally doing dimensionality reduction with principal component analysis. So PCA is built on linear algebra. So I'm hoping that you have some comfort with a lot of these concepts. It's probably worthwhile going back reviewing, but I'm going to try to make this presentation as self-contained as possible. The basic idea behind PCA is I want to figure out when we've got our data embedded in some sort of Euclidean space of possibly high dimension. You want to understand if there are sort of trends or correlations within the data, which then allows us to extract and work with a lower dimensional subspace. You'll note from 2 lectures ago, we brought up this issue of the curse of dimensionality. And so being able to reduce our data's dimensionality is a really important thing to do, because then we can always apply then further methods that sort of piggyback off of PCA, such as k-nearest neighbors. But let's start off with the most basic example where dimension is not too high. So suppose I hand you this sort of scatter plot of feature vectors associated to a bunch of samples. So I'm organizing or collecting data on X and Y information, which maybe you think of as height and weight or some other features. So one thing to note is that this data seems to be pretty tightly clustered around the x-axis, which leads you to believe that maybe this data isn't sort of truly two-dimensional, even though we have used 2 feature vectors. And indeed, if we had data that kind of looked like this, where it seems to be clustered or clumped around some line, we would also say that this data is not really truly two-dimensional. And in fact, that we could use a single sort of independent variable and then determine the other one as a response variable, just as we do with regression. So correlations between our feature vectors is essentially some way of getting at how we could maybe reduce data. So by considering some feature vectors to be linear combinations of others, we have an opportunity to possibly work with a lower dimensional set of features. And so PCA is all about that. All right, so let's go through a quick linear algebra review. So linear algebra sort of has both a mechanical, here's how you work with matrices, and a theoretical perspective, which is thinking of matrices as actually operators on some vector space. And it's useful to have both these perspectives in mind because we can often deduce facts about matrices by stepping back and taking this sort of more theoretical perspective. One of the most important results from taking this more general or theoretical perspective is that certain quantities associated to matrices are invariant, even though it might be hard to show that directly. So for example, if you think of the trace of a matrix, which is the sum of all the entries along the diagonal, this turns out to be invariant under what's called change of basis. Similar thing is true for the determinant of a matrix, which at least in finite dimensions is what determines whether a matrix is invertible or not. The key observation to have in mind, what separates sort of mechanical linear algebra, where you're just like dealing with operations on matrices, and sort of more theoretical linear algebra, is that when you're working with a matrix, you're working with an explicit choice of basis of both the sort of domain of your vector space and the range of your vector space. And when you're looking at sort of square matrices, you can think of this as a map or matrix that takes one vector space into itself. One of the beautiful things about linear algebra is that you can free yourself of the matrix by trying to work with quantities which don't actually depend on you choosing a basis. So what is an example of this? So if I have some matrix, and I can think of this matrix as what's called a linear operator. If I see how it acts on a given vector, and that vector is returned to itself, but possibly scaled by some value, lambda, and that's why these numerical quantities are called scalars, because they scale your vectors. If you have something like this equation holding true, then what we say is that assuming v is a non-negative or a non-zero vector, that this is an eigenvector with eigenvalue lambda. So that's what it means for a matrix to have an eigenvalue, and in particular, when it does have an eigenvalue, what is the associated eigenvector? Another concept which is really important is this notion of diagonalizability. So this turns out to be the thing which really makes the sort of theoretical perspective of linear algebra really useful. So a diagonal matrix is one where you have only non-zero entries on the diagonal entries. So everything else is zero outside of the diagonal. So it looks very simple. In particular, if you look at how a diagonal matrix acts on the first basis vector, where you just have one and that first entry, and then zero is all the way down in the column. It just returns whatever, it scales it by whatever's in that diagonal entry in the first location. And similarly, as you march through. So a matrix is diagonalizable if there's some invertible matrix. We think of this as our change of basis. That allows us to sort of rotate our perspective so that the way this matrix operates is just purely by scaling its basis vectors. And so the whole business of diagonalizability is finding this sort of right basis vector, change of basis matrix. So just a little bit more terminology. So remember that a matrix is symmetric if it's equal to its transpose. Now this is something that really makes sense when you're dealing with mechanical linear algebra, where you're writing down actually sort of columns and rows of numbers. The transpose is just where you sort of flip rows and columns. So you go from like an m by n matrix to an n by m matrix. And if those are equal, then necessarily this matrix is square. It turns out that there's also a sort of theoretical notion of what it means to be a symmetric matrix, but we won't get into that. And then finally, we have this notion of orthogonality. So remember, when you think of this matrix multiplication, what you're doing is you're taking sort of row vectors in the matrix on the left, and you're taking dot products with column vectors on the right. And if you happen to do this with a matrix in itself, viewed as sort of taking P times P transpose, you get back the identity matrix. This means that all the columns and rows are sort of orthogonal, or all the columns are sort of orthogonal to each other, except for itself. that sort of dot product with itself is then giving you the norm. So that also says that this is a unit length vector that populates the columns of P. This also has the consequence that the transpose is the inverse of the matrix. All right, so this result sometimes goes under lots of different names, but what's important here is the concept. And the concept is that the issue of whether or not you have eigenvalues or you have enough eigenvalues or in corresponding eigenvectors is very intimately connected with this notion of diagonalizability. This kind of makes sense. If you have a diagonal matrix, then you automatically have a basis of eigenvectors where all the eigenvalues are just the entries on the diagonal. Just remember, I take that 1, 0, 0, 0, and I apply it to my matrix. I just get back 1, 0, 0 times whatever that entry in that first coordinate was. And so it turns out that this is part of a if and only if result. And in particular, a matrix is diagonalizable if and only if it has n linearly independent eigenvectors. So that is that notion of a basis being linearly independent and spanning. All right, so this for symmetric matrices, we can go even further. And in fact, it turns out that being a symmetric matrix automatically implies that you can be diagonalized. And in fact, diagonalized using a very special change of basis matrix, one where the columns of this change of basis matrix are orthogonal, or they form an orthonormal basis. So we say if A is symmetric, then A is orthogonally diagonalizable, which means there's this orthogonal matrix P, such that A is equal to P times D times P transpose. So of course, if I multiply both sides of this equation with P transpose on the left and P on the right, then I can express my diagonal matrix as equal to P transpose A times P. So the entries of D are given by, and it turns out these are necessarily real eigenvalues. So this diagonal matrix that's associated to A encodes all the eigenvalues, and all the eigenvectors are the things which actually determine the entries of P. So you can think of the spectral theorem as telling you that being symmetric is sufficient for being orthogonally diagonalizable. But in fact, we could show it's necessary as well. So let's just assume that I'm given a matrix A, and I know that it's equal to P times D times P transpose, where P is an orthogonal matrix, D is diagonal. So if I just carry out what is the transpose of A, assuming this equality holds, then I could take my transpose, and I have to remember that when I take the transpose of a product, it turns into the reverse product of the transposes. So X times Y, all that transposed is Y transpose times X transpose. So doing that here, you can see that, so if I think of this P transpose as Y, and I think of P times D as X, then first I have to switch Y and X. So there's P transpose, and then I've got the transpose of X, which then again also flips. And you can see from the fact that transpose could give you back P, you actually end up back with A. So just by going through the mechanics of taking transpose symbol, you could conclude that A transpose is equal to A, meaning A is symmetric. So orthogonally diagonalizable implies symmetric, but also symmetric and real implies being orthogonally diagonalizable. So how does this relate to data analysis? Well, one of the most fundamental units for doing data science here is we think of the matrix as being the thing which sort of populates observations or features of a sample. So we have samples that are populating our rows, and each of the corresponding features are corresponding to row entries. And so very often the number of features and the number of samples aren't the same. So we're not going to get a square, far be it from symmetric matrix. So one thing you can do is if you have just an arbitrary real m by n matrix, you could take A times A transpose. And that is going to actually turn out to be a symmetric matrix. Again, just for the very reason that when you take the transpose, it switches, and then transpose of the transpose is back to itself. So this and this are going to be symmetric matrices. So just real quick to make sure you're following along, what are the dimensions of these matrices? So what happens when you multiply these matrices together? I want you to think about that for just a few seconds. Okay, so basically, if A is m by n, then A transpose is going to be n by m. And so this is going to be an m by m matrix, so Mike by Mike. And this is going to be an n by n, nano by nano size matrix. All right, so let's just figure out a few more little observations, and then we'll get into some of the code and what PCA is made of. All right, so here's an interesting fact. So if I take my m by n matrix A, and multiply it by its transpose to obtain an m by m matrix, even though this matrix and this matrix have different dimensions, one is m by m, the other is n by n, then these have the same eigenvalues. So just to try to prove that for yourself, consider if V is an eigenvector of A times A transpose, then if I take A transpose V, this actually serves as an eigenvector of this other matrix, where I have A transpose times A. Just to see why, well, we assume that A times A transpose V is equal to lambda V. So it's an eigenvector with eigenvalue lambda. And now I'm going to take A transpose V, and I knew I had to do something like this just for dimension reasons. V here is a m by 1 matrix, so it's a column vector of length m. And then A transpose is going to turn that into a n by 1 matrix, so a column vector of length n. And then if I apply that here, I've got, okay, A transpose V. Well, I already know that that's lambda V. So this expression here collapses to lambda V. So I can pull the lambda through because it just scales. This is a matrix. But then I'm left back with an A transpose times V. And that's exactly the candidate eigenvector that we wanted. So, all right, so let's just quickly verify some of these results using some randomly generated data. And of course, using the principles behind Python and NumPy. All right, so what happens here is I'm going to just generate a random matrix, 200 by 3. And let's go ahead and check what all these dimensions are just by taking these sort of shape summaries of each of these guys. All right, so here we have 200 by 3. That's the shape of A. So that's 200 rows, 3 columns. And so consequently, if I do A transpose, which I represent as A dot T, then that's got the reverse. So it's got 3 rows and 200 columns. And then if I take A matrix multiplications, that also is encoded by dot, A dot transpose, A dot T. So this is A transpose. Well, that's going to have 200 by 200 size shape. All right, so just to confirm everything we just looked at. So let's imagine we do A times A transpose. So remember, our prediction here is that A times A transpose should be a 200 by 200 matrix. So let's check. Okay, so we've got a lot of entries. And again, all these things are sort of randomly populated. Now what happens if we do the reverse? We do A transpose times A. then this is a 3 by 3 matrix, exactly what we predicted. So already we have a really remarkable fact just from that sort of like more observation slide, which is that even though these matrices have radically different sizes, they actually have the same set of eigenvalues, which is pretty amazing because a 3 by 3 matrix can have at most 3 eigenvalues. And this one can have at most 200, but it turns out that a lot of those are repetitions. So let's go ahead and see this. So I'm going to call E1 to be NP. This brings in the linear algebra model. And so this .eig method on A transpose A is going to have sort of two sets of data. So it's actually have 2 arrays. First is an array of the eigenvalues. And then it has associated to these, the eigenvectors associated to these eigenvalues. All right, so remember that we have 170, 13.2, and 19. So if our prediction is correct, when I do this method applied to A times A transpose, I should have these 3 eigenvalues also in that list, but it's going to be among 200 eigenvalues. So let's go ahead and do that. Oh boy, so what do we got here? So you can see here that we've got 1.7 times E02. So remember that's 10 squared. That's basically what that means. So that's 170. All right, so let's remember. Yeah, good. So we had 170.8. So that's our first eigenvalue, but written in scientific notation. And because of sort of numerical, rounding, it's tempted to think it's actually got complex eigenvalues. That's represented by J, the square root of -1. And then similarly, all right, so 1.95 e to the 1. Okay, so that's 19, good. 1.9, and then I've got this 1.32 e to the 1, so that's our 13.2. Well, that's very good. So those end up being our first 3, and then all these end up being essentially 0. So that's e raised to the -14. But these are numerical methods, so they're not gonna necessarily know all the theorems of linear algebra. All right, so that was a quick review of basic linear algebra, and we're gonna make use of those concepts shortly. But we're also going to bring in some concepts from probability and statistics. And remember, we did a little bit of review a few lectures ago. But let's go ahead and remind you of some of these things. So suppose we're measuring a single variable of say people, like their height. And so when we take these in measurements in different people and measure their heights, what we're doing is we're taking a draw from a random variable, which is a person's height. We can't perfectly predict someone's height. It's a quantity which varies. But we could pull out some summary statistics from this sample of these n heights that we've measured. So one is the mean, and that's where you just add up all of these guys and you divide by n. But then we've also got things like the population variance. And so what this is I take my mean, that gives me a number mu a, and then I look at how far each of these numbers is from that mean. It sort of tells us how spread out our distribution is. And again, we average over this. This just reflects the fact that the variance is really an expectation of the square distance from an observation from its sample or from its mean. So we also have this notion of sample variance, where instead of dividing by n, like we would with mean, we divide by n-1. So we just use, this comes from sort of on high from the fact that when we want to try to actually estimate some of these quantities, like variance of a distribution, it turns out that it's, in order to get an unbiased estimator, we have to actually divide by n-1. And that's a pretty subtle result, so don't worry about understanding exactly where that comes from. So sort of stepping back and taking a broader perspective of where these things come from. So imagine we had full access to a random variable. That means we know all possible values and the probabilities of each of these values, at least in the case of a discrete random variable. Remember, we had this PMF table. Then the expectation or mean is just I sum up the value times the probability of that value. Now in the continuous case, so this goes to random variables which are continuously distributed. You can instead use this integral formulation, and in place of the probability mass function, the PMF, use this probability density function, f of x. And so you go from there to then define that the variance, the true variance, not one that's obtained from a sample, comes from applying that formula for expectation E, but to this shifted random variable where I then take x minus its mean, and then I look at actually that squared, and that gives me a new random variable. And so one of the beautiful results is that if you want to understand how the sum of two random variables varies, we have this relationship that it's not quite the sort of Pythagorean theorem, because there might be sort of covariance, which sort of tracks how correlated two random variables are. So this variance of the sum is actually the sum of the variances plus 2 times the covariance. And this covariance is defined as how does the deviation from the mean of x, so that's x minus mu x, and how's the deviation from y covary? So meaning when I take this quantity, when it's positive, is it true that this tends to be positive as well, or does it not matter? No. And so correlation is, in a sense, detected by covariance. And again, we just went over, if we're doing this now for a sample, like when we would sample, say, heights and let's say weights. So A was our sample of heights, and B is now our sample of weights. And I compute this sample statistic, which is, I take the product of a person's height minus the average height and their weight minus the average weight, and I sum all this up. What is this number? And if this number tends to be far from 0, then we have good reason to believe that A and B are correlated. All right, so we've done everything we need in order to start the PCA pipeline. So remember, PCA stands for Principal Component Analysis. And again, the thing we need to start with is a matrix. And this matrix we can think of as being extracted from a data frame. And the features of this matrix are that my rows are indexing my samples. So that you would think of this as, say, the number of people I interview to then measure things like their height and their weight. Those features, height and weight, for example, are then the things that index our column vectors. So in this setup, if we have m rows, so m this way, and we have n columns in this way, then what we're looking at is we're studying a population of m samples, but we're now measuring n features. And this means that we embed our samples as points in an n-dimensional vector space. And that's all encoded in this matrix D. Now notice D is not diagonal like before. I'm just thinking of D as data. So you could also think of these as basically my m different draws of n different random variables, f1 through fn. Those are features. And so we're trying to summarize some statistics about this sample across all these different features, but collected across the same sample of individuals. All right, so one of the first things you always need to do is you need to mean center your data. So what that means is, and no pun intended, we need to take each of our samples viewed as a row vector, and then just go ahead and compute the mean across that row vector. So take my first row vector, add it to my second row vector, add it to my third, all the way up through m, That's what these guys are. And then I divide by m. And that's going to tell me the mean, the sample mean, my first feature, the sample mean, and my second feature, sample mean all the way up into my nth feature. And so we can then recenter our data to then see if particular samples are above or below that particular feature as mean by treating this entry u1 as a column vector filled with mu1s, and do that all the way up through mu n. And so then I subtract from my data matrix this column of means for each feature. And this is going to have the effect of mean centering my data. The consequence of that is if I were to repeat this procedure with B, I would actually get B back because then the means would be all 0 once I've mean centered my data. All right, so let's see how this works in action. So I've kind of created this data frame a little backwards just because I wanted to enter in my samples as my keys of a dictionary. And then I looked at gene expression values as my sort of features associated to each mouse. Mouse 1 all the way to mouse 6. I'm measuring expression levels of these two genes. Now, in order to make it turn around the way I wanted it to, I had to apply this dot transpose method to get my data. So data is equal to this mice pandas data frame transposed so that my mice index my rows and my genes index my columns. You can see here that index is normally given by gene 1, gene 2. So if I were to just show you how this works briefly, mice, it would look on its side, but now I have data and I've transposed it. All right, so let's just go ahead and run through all these steps. So I'm going to go ahead and comment out. See just what happens when I apply this mean method to my data frame. So it knows exactly what to do. It goes across all my mice and computes the mean of gene 1's expression value, and then also computes the mean of gene 2's expression value across my 6 mice. So let's go ahead and hide that. And now let's do exactly what I said. So B equals data minus mean. And it's going to know what to do here. So let's go ahead and just look at that. So that's pretty nice. It's gone ahead and taken my mean and subtracted it from each of these guys. And so we can see that mouse 1 through mouse 3 tend to have above average expression levels. And mouse 4 through mouse 6 had below average expression levels for gene 1 and in fact gene 2. So this leads us to believe that maybe there's some correlation between expression level of gene 1 and expression level of gene 2. And so this can be visualized by looking at the scatter plot associated to this feature vector. This feature vector consists of expression level of gene 1 and expression level of gene 2. And that allows me to create a scatter plot of my samples. Okay, so again, the goal here is we believe this data is actually sort of one-dimensional because there seems to be a tight correlation between expression levels of gene 1 and gene 2. Let's try to formalize that using PCA. So recall, we've now mean-centered our data. So we've taken our matrix B, which corresponds to all of the samples for feature 1. Again, that's indexed by this column right here. We've subtracted off the mean for column 1 and gone through and done that for each column. And so we're now going to look at B transpose times B. So B transpose just consists of the transpose of B, which is our mean centered data, and we've multiplied it on the left. Now, of course, we know that this matrix is now symmetric. And just take a moment to convince yourself that that has to be symmetric. All right, so assuming you've done that just fine, you can see that now if I go ahead and look at the spectral theorem, I've got a symmetric matrix, that means I can diagonalize. But let's go ahead and try to interpret what are the features of this diagonalizable covariance matrix, and why did we choose B transpose over B, B transpose times B rather than B times B transpose? Again, take a moment to think about that for yourself. Okay, so the basic answer is that we're trying to create something that is intrinsic to feature space, where we've got n-dimensional features, and we want to have all our plots and our points and our sort of correlations to be measured in feature space rather than sample space. But again, we can work with both perspectives. And in fact, this is sort of summarized now on the following slide. And this is really the heart of principal component analysis. So the spectral theorem tells us that C, which is this 1 over n minus 1 times B transpose times B, can be diagonalized. And we know that its eigenvalues consist of these real eigenvalues. So that means they're all, elements of the real line. And we can order them so that we have our largest eigenvalue, and we label that lambda 1, and then our next largest lambda 2, so on and so forth. And corresponding to each of these eigenvalues, we have eigenvectors u1 through un. These are called our principal components of our data set. And so we think of this as these being the directions where actually most of the variation occurs. And we're going to make that precise in just a second here. So just as a quick reminder, so I remember I did my mice data, and I subtracted the mean to get B. And so now I'm gonna look at B transpose times B. And so I've got, again, so that I had 2 genes. So now if I do this B transpose times B, I get a 2 by 2 matrix. And so I have at most 2 eigenvalues, 106 through 4 and 4, and these are my 2 associated eigenvectors. So we're going to try to understand what the meaning of those eigenvectors are. Notice that we didn't divide by n minus 1. So I'll leave it to you to think about why we did that or didn't do that. All right, so the answer is somewhat baked into this slide here, but I want to also just go back and point out that if I look at this eigenvector here, it's one where so this is my my second eigenvalue. This is the one that sort of seems to be varying the least, and that's the one that sort of corresponds to our positive slope. But we'll go through that again in more detail. So just moving on. So remember, when I've got my matrix B transpose times B, it's my mean centered data B, right? Then multiplied by B transpose on the left. Now, if you sit down, you look carefully at what's happening in that mean centering process, and then what this dot product looks like when you look along the diagonals of this product matrix, you'll see that the sum of the diagonal entries consists of the variance of the first feature all the way up through the variance of the nth feature. And so in particular, because these all consist of squared numbers, this ends up being non-negative, and as are all of these. So this just sums up a bunch of non-negative numbers, which is some of the variances for all n random variables, which correspond to our n features. But remember, we know that the trace is an invariant. So if I looked at now the trace of the diagonalization of B transpose times B, which exists by virtue of the spectral theorem, then I have the sum of the eigenvalues is equal to the sum of the variances. And so since I order my eigenvalues from greatest to least, I could think of lambda1 as being the eigenvalue, which corresponds to like the largest amount of variation. And in fact, that's expressed as a percent by lambda1 divided by t, which is trace. And that we use that as a proxy for noticing in what direction does our data vary the most. And we'll understand exactly why that is in a second here. Therefore, mu1 points in the most significant direction because that's the eigenvector corresponding to lambda1. So then once we're going to take that eigenvector as our sort of basis for which we want to describe our data, we can then look at smaller eigenvalues, which are going to explain still some, but less of the variation in our data. And here variance is really meant, variation in data is meant precisely in the terms of probability theory. So let's go ahead and just extract out what's going on here. So T is going to be the sum. So remember the 0th entry in that list produced by that eigenvalue method is going to be our array of eigenvalues. And so this just sums up the first and second eigenvalues. And so now we can just go ahead and extract out each one of these. So notice that we've got here our first principal component consists of, we look in our second item in our eigenvalue list, which now gets into the actual vectors, and we look at the things that correspond to the first column. So that also tells you need to make sure you read this matrix along columns and not anything else. And so you can see here that when we look in this direction of 0.94, 0.33, so that corresponds roughly to a line of slope a third, maybe a little more, which is exactly the line that kind of passes through along this way. So our principal component of variation occurs along this line that is given by this equation. And so then the second principal component, the one that explains the second most amount of variation, is orthogonal to this. Again, this by virtue of the spectral theorem that these vectors are orthogonal. And so when I look at the dot product that goes this direction, you can see there is much less variance. And in fact, only 4% of the variance occurs in this direction. 96% of the variance occurs in this direction, which makes sense just visually. So that's our mice data where we've applied the spectral theorem to our mean-centered mice data. All right, so as a high-level overview, we're collecting, sorry, this should be transposed. This should be M samples of n-dimensional data. My apologies. Compute the mean, mu, and subtract it from your data matrix, and then compute the covariance. And then once you apply the spectral theorem, we now have our list of eigenvectors and eigenvalues. The eigenvector that corresponds to the largest eigenvalue explains the most variation in our data. And so one thing we can do to then reduce the dimensionality of our data is by then just projecting onto the first k principal components. So if we've got some really high dimensional data, let's say n has 100 features, but we find that actually the bulk of the variation occurs in the first 4 or 5 principal components, then we can project onto those components and only lose so much structure in our data. So let's see how that works out in this toy example with the mice. So as a reminder, remember, if you want to project onto a subspace, and so in this case, we've got our first k eigenvectors ordered by eigenvalue size, then we can let W be the subspace spanned by these vectors. So these are our k eigenvectors, first most prominent k eigenvectors. And so the formula for projection says that, okay, if I have a matrix whose columns are V1 through Vk, then any vector x projects onto this via this formula. So this takes a little bit to really understand, but you should review, for example, this construction, which we'll go through and explain in more detail how this projection occurs. And you can start with just by projecting onto the line and then figure out the general method. All right, so returning to our mice example. Okay, cool. So here I just go ahead and I take a NumPy array with all the entries I want. And I just did a scatter plot of essentially that. And there are some options I can activate, but the PCA method, which just lives inside of scikit-learn dot decomposition as PCA. I could go ahead and pick number of components to be 2. And in this case, it's not going to do anything with PCA because I'm using the same dimension as the data was already given to me in. But let's go ahead and see what happens when I go ahead and just use one component. Let's see what this looks like. So I'm going to let that be my transform data. And let's go ahead and look at this. So what ends up happening, and I'll leave it to you to read this code in more detail, but essentially I've started off with my original mice gene expression data. I identified the principal component was in this direction. And then if I project onto this line, you see that each gray point or blue point goes to its corresponding orange point. And so you can see I've essentially been able to ignore the little oscillations that occur perpendicular to this line and been able to maintain a pretty faithful summary of my data along just one dimension, which is lying along this line. Okay, so I know there's a whirlwind tour of linear algebra and probability theory and quick introduction to how you can actually use this to reduce data. We'll use PCA as part of a pipeline in later lectures in this course. But for now, I think it's enough to try to chew on and look forward to seeing you all in class.